Good morning, guys. So today I'm here with a new topic, isomerism and its type. In our previous videos, we have learned about stereochemistry, and in which we have done many terminology that are being used in the stereochemistry. We have learned that also, like optical activity, chiral, acyl compounds, anisomers, DNL nomenclature, like this. So there are some different type of terms that we have used. But for this, we should know, right, what is isomerism its type. So in this particular video, we will talk about the types of isomerism and what is isomerism is. So I'll start with the very few this definition. That what is stereochemistry that we have already done. It's a branch of chemistry which deals with the three-dimensional structure of the molecule and their effect on the physical and chemical property is known as stereochemistry. So to represent, we have this. There are two structures. This is a 2D drawing and this is 3D drawing. What is the difference? Here you can see this chlorine and bromine with the represented as a solid eye. But here they are having different. This means one bromine is, in front of the observer and the chlorine is away from the observer. This is how we can represent three-dimensional structure. But in today's topic, we are going to talk about the isomerism. Basically, what are isomers? Having same molecular formula or the chemical formula but different structures. Why they are different? Because their arrangement of the atoms is different in both the compounds. They are having identical formula, but their properties will be different. And we designate both in a different Arabic name. So, therefore, these compounds they exhibit isomerism and also known as isomers. Iso means same and mers means parts. So equal parts they have, but arrangement will be different. This term is coined by Swedish chemist Jacob Religious in 1830. So it was very, very, it was not a new concept that we are dealing with. It is a very, old one. And in this, uh, in this particular video, we will talk about the isomerism, how they are and how we can represent and how we can get to know that what type of isomerism it is. As isomerism of two types, structure isomer and stereoisomer. This one, the chain isomer, positional, functional, metamerism and tautomerism and ring chain. But the stereo is having geometrical and optical isomer. So in structure isomer, we are saying the different functional groups can be linked in different ways or their arrangement can be different. So because of the functional group, rearrangement, they can be have different Arabic namings. So let's talk about the first. This is a chain isomer. In chain isomer, it will be called, it is a skeletal isomerism in which the component of these isomers, they differently, display different branch structures. Like commonly they are of carbon chains. Like this is a carbon chain, 1, 2, 3, 4, and 5 carbons are there. These 5 carbons, if they're in a longer chain, they can be normal pentane. But when suppose this carbon is going to be here, now it is not normal. Whether carbon number is same, it is 2-methyl butane, or we can say isopentane. But similarly, if this is also going to be there like this, so now its IUPAC naming will be changed because of more the branching. Okay, more different structure will be displayed by that particular carbon chain, and this type of where we are just breaking out the chain and branching is there, we call them as a chain isomerism. Now, next is the position isomer. In position isomers, what will happen? Here, position of the functional group or any substituent atom are different in the position. Like, suppose, if I'll take one example, here this chlorine is here with the first carbon. This is first, second, and third carbon. So here 1-chloropropane is, is attached to the uh, first carbon, that we call it as the 1-chloropropane, and in the second, here it is attached to the second carbon, and this is called 2-chloropropane. Means here this chlorine, that atom, particular atom is having a different position. Because of that, chemical formula is same, C3S7 and Cl, but different isomerism is there. Okay, attachment of the functional group. Now, what is functional isomerism? What will happen when functional group, a particular functional group, like it can be CHO group, aldehyde group, alcohol group, or anything. When particular, functional group is getting attached or with the different ways, like this is an example of in which you can say C3S6O, where it is propanone. On means it's a ketone. Okay, it is ketone, first, second, and third. But when it is attached to this first, second, third, now it is not ketone, it is aldehyde group, CHO. Here it is CHO and here it is C double bond O. So when a functional group, we can say it refers to the compound that have same chemical formula but different functional groups attached to them. So it is called a functional isomerism. This can also, one example, you can say it's a propanol. This is aldehyde group. But when this C double bond group is here, now it become propanone, that is ketone group. Similarly, this OH group is when it attached at the last, then it is ethanol. And when this O is here, then it is dimethyl ethyl. But the chemical formula is same in both. So how we can say that this is a functional group isomerism. Another topic here, this is also the subtype of structural isomerism, that is metamerism. This type of isomerism, they are present due to the presence of different alkyl chain on the side of any function group. This is function group. Here you can see there are 2 carbon chain on the both sides. But here this is 1, but here is longer carbon chain. It is 2, 2, but here it is 1, 3. So because of this, their iopic naming is getting changed, like ethoxyethane or methoxypropane. This is methoxy and this is 3-carbon propane, but it is ethoxyethane. So this is the general, very rare type of isomerism, and it is generally limited to the molecule that contain divalent atoms, such as sulfur, oxygen, and they can be studied by the alkyl groups. What type of the different chains are present in the left and the right side of that particular group. Another condition is tautomerism. It is also another type of isomerism. Here, a tautomer of a compound refer to the isomer of the compound, which only differs in the protons and the electrons. So basically, they are different in the protons and the electrons position. So how we can say it is basically they can be very easily interchangeable. That's why this equilibrium sign is there. That means I'll let you know what is tautomerism. First of all, basically it is a intermolecular proton transfer condition in which if this proton if will be transferred to here, then it will become OH. But if this bond is transferring it, so it will become enol form. This is a keto form because ketone group is here, C double bond O. By why it is enol? Enol means ol. Ol means OH group, like alcohol form. So it is very important part of chemical reactions formula, where in this phenomena keto and enol form they are getting interchanged because the position of the proton or electrons is getting changed. So something is getting changed Like every chemical formula is same, that is called isomerism. So this is called tautomerism. We call it as keto-enol tautomerism, in which keto and enol groups are in equilibrium. You can see here, this is the alpha hydrogen, which is if it is getting transferred to this side, so what will happen? So this keto form, because of this ketone, now getting converted into enol form. So in this, we can see this how this keto and enol forms, they are getting changes. Okay. Now the last form is ring chain isomerism, in which one of the isomer has open chain, whereas another has a ring-like structure, but the number of carbons are same, 1, 2, 3. Okay, it means C3S6. It is also C3S6. It is also C3X3. But the arrangement and their pi bonds, they are having different number of pi bonds. They contain a different type of, changes in that. So propene and cyclopropane, they are resulting isomers, and they are also called ring chain isomers. Okay. Now the second part of type of stereo that your isomerism is geometrical isomers. So basically geometrical isomers have same structure formula because it is isomers. Structure formula will be same, but what will be different? They are different in their spatial arrangement around the double bond. So basically, if you will see this example, this is carbon and this is another carbon and having a double bond. Now, if you will see the position of the groups which are attached, here methyl group is attached in the same direction, hydrogens are on the same. So if you will say, if the arrangement of the atoms or the group of atoms are on the same side, we call them as cis, and if they are on a different side, like this, diagonal side, so we will say they are trans butene. So it is a cis butene and that is a trans to butene. These are what they are basically. They are geometrical isomers where spatial arrangement is different around the double bond. Okay, so how we can say that they are cis and trans according to if they are on the same side, same group, this is, if they are on a diagonal, then they are trans. So these two form basically they are interconvertible due to the restriction of they are not, they can't be rotated themselves like this or this. No, because of the double bond doesn't allow them to interconvert. So in cis isomer, okay, in cis isomers, groups will be on the same side, but trans isomer, they are on the opposite side. So, very important point to be noted here, that is, trans isomer of the compounds are usually more stable than the cis isomer. So, this is cis and this is trans. Same groups on the same side, same group on the different side. Because of the steric hindrance, cis is not much stable, but trans is having more stability. So, another second example, there are two geometrical isomers, cis and trans, they are possible in one for dimethyl cyclohexane. So here, the groups are on the same side, they are cis. Here, they are on a different side. You can check here. Then they are trans one. So these isomers, they are not interconvertible, but it is impossible to rotate the bonds in cyclohexane ring also. So it is, the question is, why, why it is happening? What is the cause of geometrical isomers? So basically what happened, the pi bond in carbon-carbon, this pi bond in this carbon-carbon double bond by sidewise or lateral overlapping of two p orbital. This is also called p orbital. This is a p orbital. Okay, they are, overlapping, sidewise overlapping. When one of the double bond of the carbon atom is rotated about the double bond, the pi bond breaks and parallel p orbital does not remain parallel. Here you can say this one. But when rotation is completely 180 degree, the p orbital again become parallel to each other, and hence pi bond is formed. So this is due to the breaking and reforming of the pi bond. First they break and then they reform after the rotation. Due to the restricted rotation about this carbon-carbon, new configurational isomer is formed. So this is basically a breaking and reforming. This is a breaking and reforming of pi bond by 180-degree rotation of one of the two double bonded carbons. So configuration, basically the optical and geometrical isomers are basically a configuration. These are isobel and not easily interconvertible from one another. These are configurations. So the question is, can we can we determine the configuration of geometrical isomers? Yes. How? First technique is melting. Suppose you have one cis compound and another is you are having trans compound. Now the question is melting point. How it will decide that who is cis and who is trans? So you will note the melting point. Trans isomer is higher than that of the corresponding your cis isomer. Why? Because the reason is trans molecules in the molecule of trans isomer, they are more symmetrical and hence fit more closely. There is no steric hindrance. Because of the more stability, the temperature or the melting point will be higher. So in order to intermolecular forces to work well, molecule must be able to pack together efficiently in soil. So in case of trans isomers, they pack better than the cis isomer. So we can check the whosoever having the higher melting point, they will be trans one. So here you can check that the example here. This is UH. This is cis. Melting point is 403 Kelvin. But here fumaric acid, where it is in a opposite directions. It is a trans isomer. Melting point is more than the cis one. So this is one example. So because of the poor packaging in the cis isomers, intermolecular forces are not that much effective. And because of that lower energy, they need, so lower energy is needed to melt them. And because of that, they are having lower melting point. Another is solubility, basically. So solubility, if I check that this isomer solubility will be more than the trans isomer. Why? Because in cis isomer, they are less tightly be held by in a crystal lattice. They are not closely packed, so they can be easily be soluble. So that's why we will say in case of cis, the molecular weight is 79 gram and Dremel and in fumaric acid, it is 0.7 gram per 100 ml. And in dipole moment, if I'll talk about cis isomer has dipole moment, then corresponding trans isomers. So, in dipole moment, if you will see, in case of cis, dipole moment is 1.85. But in trans, because they cancel out their effect, the dipole moment is 0. So, cis isomer have higher dipole moment than the trans isomer. Okay, so we were talking about the methods are being used to differentiate between cis and trans. So here stability. Trans isomers, we have already told that it is more stable than your cis isomer due to the steric hindrance, and they cannot rotate around the you will say the double bond. So here you can say this is a test when you cis and when you will heat at 160 degree, then it is getting changed into butyric acid. Okay, and in trans, they are this fermanic acid, they sublimize on the heating, but no chemical change is there. They are stable. Okay, so action of heat is required here. If you will, check the differentiate between cis and trans. On strong heating, cis and trans isomer are interconvertible. So this interconversion takes place as follows. Homolytic bond fusion will be there, and they will be this A, double bond is breaking, and then A is here, and then A and A. That means this is cis isomer plus trans isomer. Okay. So in this case, you will see how they are getting changed. Uh, Now we have seen that what is cis and trans, but in this we will talk about E and Z notations for geometrical isomers. But if there is a cis and trans, then why there is a necessity to having E and Z notation? So there is something that is I'll let you know that how cis and trans are different from E and Z. Whether both are used to for the notation of the geometrical isomers. So what happened basically? It is very simple to donate cis and trans when the groups of the same on a double bond, the same side they are cis and or they are on a opposite side they are trans. To differentiate in them, a new system of nomenclature will come. That is E and Z notation. So according to this method, if the group with higher priorities are present on the opposite side, the double bond, then they are these isomers they are say called as antagon, and it is noted by E, means opposite. High priority groups are present on the opposite side. Okay. What happens basically sometimes in double bond, there are different, you can say, suppose in case what will happen, double bond is CH3, CH3. But if suppose there is no H, here it is Cl, and here it is something Br. So it's different. If different groups are attached, then we require this system in double bond C, double bond C. But if the groups of higher priorities are same side, the double bond isomer is denoted by Z, and it is zoosamine, means together. So E and Z they represent within the molecules, and we can say separated with the different names. So now first determine how we will get it. You have to first determine the higher priority group on each end of the double bond. If higher priority groups are on the opposite side of the double bond, then we will say it's E. And if they are on the same side, then we will say it is a Z, zoosamine. So now just take the first rule for this. This is high priority groups, iodine. All groups are different. So that's why we require this E and Z. Iodine and bromine is having high priority on the same side. So they are Z. And here they are on a opposite side, then it is E. And if the isotopes are there, suppose this is HD means deuterium. And this is hydrogen. Obviously, they are different. In this, they are on the same side, higher priority groups. And here, they are on a different side, opposite side. Then it is E. So rule number 3, if you will see the longer carbon chain, they are on the same side, they are on a different. But here, in case of E, means CH2, CH2, CH3 is having higher priority than CH2, CH3. In Z isomer, here, bromine is there, here is a chlorine. Okay, both are having high priority. They are on the same side, zoosamine. But here, it will be, you have to check the priority. Higher priority, this one. This is CH3, this is bromine. But here, hydrogen in this. So geometrical isomerism can also be seen in the cyclic system, in which letter E and Z are not used in cycloalkanes, first of all. And cycloalkanes, they can show cis and trans geometrical isomerism. Okay. Here, this molecule is here and this is here on a trans phase. And here, they are on the same side. So, cis. Thank you so much, guys.